In keeping with good social distancing practices, please keep a minimum distance of 6 feet from your screen as you watch this video. Thank you.
Momentum is conserved in every situation, even in a car collision. Momentum, go, 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 go. F equals ma and impulse is F times v. Momentum, momentum. Change in momentum equals impulse, see how it links. Momentum, momentum. Remember P will stay the same, so don't hurt your brain. Momentum, tum, tum.
Why is it if you throw a raw egg with a given mass at a given velocity against the wall, why is it that upon impact the egg is destroyed? But if you throw another egg of the exact same mass with the exact same velocity against something that's a bit more forgiving, some kind of screen or sheet, why is it that the egg in that case isn't destroyed? The correct answer to this question rests in a proper understanding of the impulse momentum theorem. We learned in the previous video that momentum is mass in motion, and that we can determine an object's momentum by multiplying its mass in kilograms by its velocity in meters per second. So now let's get a simple definition of impulse. Impulse is defined as the product of a force acting on an object and the time over which that force acts. F times delta t equals impulse. Now that we've defined both momentum and impulse, we can define the impulse momentum theorem. All it says is that the impulse an object experiences is equal to the change in momentum the object experiences. Mathematically, the impulse momentum theorem is stated as F delta t, that's impulse, is equal to mv sub f minus mv sub I. The right-hand side of the equation represents the change in momentum. One of the most important things to understand about the impulse momentum theorem is that for any given change in momentum, the variables force and time are inversely related. In other words, if an object experiences a change in momentum over a very brief period of time, it's going to experience a tremendous force. However, if the object experiences that same change in momentum over a much greater period of time, the force will be decreased. And it is for this reason that you can throw a raw egg at some kind of sheet or screen and it won't break. Here are two more practical applications of the impulse momentum theorem. If you've ever been around sports, you've probably heard a coach tell a player, follow through. The coach intuitively understands the inverse relationship between force and the time the force is applied. They understand that to reduce the force necessary to accomplish a task, it's going to be reduced if we extend the time over which that force is applied. Doesn't matter whether you're swinging a golf club, a tennis racket, throwing a baseball, swinging a baseball bat, or for that matter, doing something ordinary like swinging a hammer. The longer you apply the force, the less force you'll need. A second and far more important practical application of the impulse momentum theorem are airbags and front crumple zones in automobiles. Both of these devices are designed to increase the time over which you experience a change in momentum so that you experience less force. Here's the first of two impulse momentum theorem sample problems. A force of negative 5.0 times 10 to the 2 newtons is applied to a 1,500 kilogram truck for 5.0 seconds. What is the change in the truck's velocity? Let's identify our unknowns. First, we have a force of negative 5.0 times 10 to the 2 newtons. We also have a mass of 1,500 kilograms, a time of 5.0 seconds. What's our unknown? We're looking for a change in the truck's velocity. We'll start by writing our equation for impulse momentum. F delta t equals mvf minus mvi. But Since I'm looking for a change in the truck's velocity, I'm going to alter that equation slightly. I'm going to change it to F delta t equals m delta v. All that remains for us to do at this point is to make the substitution, do the math, and we'll come out with an answer of negative 1.7 meters per second for the change in velocity. Here's the second of our two impulse momentum theorem sample problems. A 60.0 kilogram woman jumps from a burning building and falls 10.0 meters before making contact with a safety net that stops her in 0.120 seconds. What is the force exerted on her by the net? Our first piece of given information is a mass of 60.0 kilograms. That's followed by 10.0 meters, which in this case is a delta y value. We've got a time of 0.120 seconds, and what we're looking for is the force exerted on her by the net. Let's write down the equation for the impulse momentum theorem and take a look at it. We're looking for force. We know the time. We know the mass of the woman, but we have neither the initial nor final velocities at this point. So before we can solve this as an impulse momentum theorem problem, we'll need to do some kinematics. I'm going to use this kinematics equation to solve for the woman's final velocity after she falls. Because I'm using this equation and treating it as a free fall, I know that her initial velocity can be assumed as 0.00 meters per second. I also know that in the absence of air resistance, the acceleration due to gravity is negative 9.81 meters per second squared. So let's make the substitution. When I take the square root to obtain my final velocity, my choices are positive 14.0 meters per second or negative 14.0 meters per second. The woman is falling downward, so the proper final velocity in this case is negative 14.0 meters per second. Due to space limitations, I'll now erase everything on here except the problem as stated, and will solve for the force exerted on the woman by the safety net. Let's write down the equation for impulse momentum. And before we begin substituting, we need to take something into consideration. We determined that the woman's velocity at the bottom of her fall was negative 14.0 meters per second. We now need to remember that that is her initial velocity upon hitting the safety net. Her final velocity will be 0. So when we make the substitutions, we need to substitute accordingly. The calculator yields an answer of 7.00 times 10 to the 3 newtons. It's a positive force, as it should be. The woman's falling down. The safety net has to exert a force in the upward direction, which is positive, in order to stop her.
Any of this getting through to you, son?